All right, thank you. Hi, I'm Ricker, a PhD student at Carnegie Mellon University. So every day we perform various procedural tasks like cooking, crafting, or medical self-test kits. Mistakes can happen, and it will lead to negative consequences. In the recent study, it is reported that 20% of people have made mistakes in using COVID-19 self-test kits. The goal of this project is to develop an intelligent agent that can monitor users and proactively intervene if they make mistakes. In HCI, there are systems designed for specific tasks, such as cooking or machine use. Often, they use cameras to track users' behaviors and present context-aware information through displays, such as using AR glasses. However, such solutions may be costly to use for daily tasks, and always using a camera can be cumbersome. Researchers have explored ubiquitous sensing, in particular human activity recognition, with a smartwatch. Prior work has used its motion and audio sensors to detect everyday activities, such as chopping a banana and washing a hand. In this work, PrISM-Observer will leverage human activity recognition to achieve situated interventions without using a camera. For example, during cooking, the agent says, hey, don't forget to put the lid after the user pours water to the pan. Or it asks, have you wiped the pan before the user cooks the next item? We assume that there are only a few key steps for the reminders within the procedural tasks, and PrISM-Observer focuses on those meaningful steps for a reminder with human activity recognition techniques, instead of trying to capture every single actions. So here's a scenario. At our department CMU, we have a fancy espresso machine shared by the students, members, which was bought by CMU faculty. Yes, they are rich. Students appreciate that, but you know what happens after that. People often forget cleaning, and there's even a Slack channel with over 150 people, and such incidents are reported repeatedly. We can prevent that kind of human error with PrISM-Observer. Here, I configure the agent to remind me of washing the filter after brewing.
Have you washed the portafilter?
Thank you. This way, I could avoid making the mistake and also being reported on Slack. So in the rest of the talk, I'll explain how to implement these interventions with just a smartwatch, which is not very trivial. First of all, applying human activity recognition to real-world procedures is challenging. If we apply an existing model to the latte making task, which consists of 19 steps, for example, the frame-by-frame tracking accuracy is very low, around 40%. The major reasons are that users perform the sequence continuously without explicit start and end moment, and that not all steps have remarkable sensing signals to distinguish from each other. In our prior work, PrISM Tracker, we introduced an approach to leverage a transition graph, which stores information on how users transition from one step to another step, and how long they usually spend at each step. This approach successfully increased the accuracy, but it is still far from perfect. Moreover, the output of human activity recognition is a frame-by-frame step information. Imagine each circle is a predicted step with different colors for different steps. The ideal order here is yellow, green, and blue, and we want to make sure that green happens before blue. So this observation, like this, it's okay because it follows the correct order. How about if the agent observes this sequence? Given its online observation, the question is, when should the agent decide to intervene the user if user makes mistakes? Maybe we could use the prediction of this step, this blue step, as at this point, the order is wrong. However, as I said, the underlying sensing is not perfect. So this could be just sensing noise. So in this case, the user may receive unnecessary reminder and may feel annoyed. Then how about reminding as a previous step? The user arrives at yellow, like saying, don't forget to do green next. It would work for a single thread task, meaning that there is no order variance. However, if there is a divergence in the transition, and the user can take other steps before actually going to the green step, the reminder becomes too early. In other words, the user behavior about the future transition is hard to predict. The core of PrISM-Observer is advancing the frame-by-frame tracking to forecasting the timing of the target step. We model this process mathematically in an abstract way, not to rely on heuristics. Recall we have a transition graph. We introduce a stochastic variable d, which indicates a remaining time from the current time to the target step. By definition, we can calculate the expectation as the sum of the value and its probability. We can further break down the equation like this. Very interestingly, this illustrates two uncertainties that the agent has, which I just explained. The first term is uncertainty about the current step, and the other one is uncertainty about the user's future behavior. The basic agent policy is that it uses the expected remaining time to trigger a reminder where there is less uncertainty. To measure the entire uncertainty that the agent has, we use an entropy of the stochastic variable, d. PrISM-Observer characterizes the user behavior with these two values, expectation and entropy of the remaining time. Let's look at some examples. So this is a graph for the actual time as the x-axis and estimated remaining time as y-axis, which is the probability distribution, and the color indicates the density. Here, the target step is S4, which is a relatively beginning step in the task. This orange line is a ground truth remaining time, which always linearly decreases as the time passes. In this case, the estimation is correct from the beginning, as there are less uncertainty, and the system accurately estimates the remaining time. Next is when the target step is S10, a step in the middle of the task. Here, there are more uncertainties in the beginning, as there are many potential transitions in the future, so the estimation is distributed broadly. The agent keeps monitoring, and at some point, around 200 seconds, it seems to capture a key step that informs the transition that user is probably taking, and thus the estimation gets more certain. Last example, when the target step is S13, the estimation is quite off in the beginning. Similarly, it could correct its estimation in the middle by finding a plausible transition based on the sensor data, and after that, that estimation becomes more certain. We crafted the intervention policy algorithm based on this expectation and entropy. For the details, please refer to the paper. We evaluated the algorithm in 3 tasks: wound care, cooking, and latte making, with different task complexities in terms of transition divergence. This graph shows the timing error for different steps within each task. Comparing PrISM-Observer and the baseline policy, we didn't use any human activity recognition. That is just a timer-based intervention policy. In short, PrISM-Observer reduced the timing error. In the paper, we analyzed and discussed the difference in the effectiveness, like failure cases for PrISM-Observer. So please refer to it. I'll show a video demo for a cooking task, which consists of 14 steps, where our user is making a sunny side up and grilling sausage. The main divergence in the transition is that whether the user cooks the sausage first or egg first. For this user, it's me, I often forget adding oil before pouring an egg. So he wants a reminder of the step. First, the agent keeps monitoring the user steps. The PrISM tracker stabilizes output of the low prediction. The agent keeps monitoring using human activity cognition. Looking at orange graph, at this point, it is not certain about whether the user is cooking egg first or sausage first. So the agent keeps monitoring. Now the agent detects the sound of breaking an egg and becomes sure that the user is cooking egg first. So it starts preparing the reminder.
Don't forget to put oil on the pan.
In this way, the user could avoid making mistakes. Future work, for now, we are focusing on using Smartwatch, which is helpful to support various daily tasks. Still, involving more sensors might be helpful for some applications. For example, ambient sensors like Doppler radars to monitor tasks at certain space. Our framework is modular, so switching the underlying human activity cognition model can be easily done. Moreover, we are integrating different interactions for the assistant, such as question answering for beginner users especially, to run and complete a task, which we call PrISM Q&A, and will appear at Imwatch journal soon. A little bit spoilers ahead. This PrISM Q&A assistant can answer users' ambiguous and spontaneous questions while doing a task. For example, like what's next? By complementing it with sensed context. Okay, what's next?
You can adjust the grind level with the knob on the left side of the machine.
Again, no camera, just a smartwatch. Users can also interactively collect agent.
Yeah, what's next?
After grinding beans, place a cup under the group head for brewing.
I did that. What's next?
After placing the cup, press the start button to begin brewing.
Right now, we are investigating this mixed initiative of the user and the assistant to achieve the shared goal of procedural task from the perspective of human-AI collaboration. Lastly, the development of PrISM Assistant is motivated by our vision of providing context-aware and situated support to patients recovering at home. For example, we are right now testing the applicability of PrISM Assistant in supporting post-operative skin cancer patients. We published our code, and let's chat if you are interested in this real-time, proactive, intelligent assistant in the physical world. Thank you.
Yeah, you come from University of Rochester. Very cool. Very nice talk. I'm really interested in the talk. I have two questions. The first one is more on the high level. I'm curious how people learn the knowledge about the procedure with this kind of technology. For example, do you feel a little bit unsafe to make a latte without wearing a watch?
Yeah, very good question. For now, our evaluation is only single shot. So that means like we didn't evaluate how user learn the task over time. That's actually what's going on right now. So please looking forward to it.
Okay. And then
What's the second question? Yeah.
Second question is like you think about different ways for the collaboration between the user and the agent, right? How do you feel like, how do you determine, what are the factors in the design space? For example, the task, the context, will there be a mapping between which is better to which task or something like that?
Mapping about like user and the agent's proactivity?
Like the relationship between the user and the agent.
Mm-hmm.
Is there like an optimal mapping between the relationship and the task or the context?
Yeah, that's a great question. So we regard this as a human-AI collaboration problem. Mm-hmm. So both users and agents are not perfect. So they have like both strengths and weakness. Mm-hmm. For example, some actions are inherently not detectable by sensors. So for those sensors, if they are really important, users need to support the agent to track the user actions. So for example, one idea is users will like self-narrate about what they're doing. For example, hey, I'm doing this task right now, blah, blah, blah. So in this like mutual communication can develop collaboration system.
I see. Thank you so much.
Thank you, great question.
Hey, I'm Marucci from University of Washington. Thanks for your talk. I just wanted to get clarification on if this agent is running on like as an app on your smartwatch or if it's like on a host machine. And if it's on your smartwatch, I guess my question was, what's the power consumption of running a network like this all the time on a watch?
Oh yeah, thank you so much. Right now the system is running on the laptop. The watch serves as a sensor streamer to the laptop. And we didn't rigorously evaluate it, measure the power consumption. We report that in the like, future publications.
Okay, thanks.
Thank you.
Yeah, hello. I'm Harish from University of Texas at Arlington. So actually, I have two questions. So I saw the demo of reminding in advance, for pouring oil or something like that. So is it done on a general perspective, or is it based on the user's choice? Please remind me in doing this step. So is it based on the user preferences, or is it done in a general perspective as per the steps followed?
Yep, I think we believe both scenarios are possible. So first of all, like if for example, like about the espresso machine in the shared space,
Yeah.
there's a system designer, like CMU faculty, because they are annoyed by students making mistakes. So they can decide, like, okay, we have to remind the students of a cleaning task. But maybe if the agent becomes more personalized, users will need to customize and the steps that they need reminder for, and our framework supports that configuration.
And also, so regarding the time measurements that you specified as part of the methodology, so is it like, did you record the times as per, like you do the task, and so based on this task, it takes this much time or something like that? Or how do you collect the data regarding the time taken?
So right now we have collected several sessions data. For example, cooking, we have collected 15 sessions from different participants. And based on that, we calculated average time spent on each step. Okay. But if the agent is deployed in the future, the agent should learn from that specific individual over time. So that adaptability is what we are investigating right now.
Yeah. So like how, like also have you taken the outliers into consideration? So something like there might be some user interventions while they're doing a task, someone is calling him or something like that. Have you taken that into account, or is it like a future work that you're planning?
Oh yeah, that's a future work. That's kind of unexpected and spontaneous user behavior. We are looking for ways to integrate that into this framework.
Yeah, okay. Yeah, thank you.
Thank you.